So, we check one more time for the translations. So if you speak English, you can hear everywhere, no problem. We have some translations in different parts of the room. Po polsku. Where's the Polish translation? You moved to the corner. Okay. Okay. Po polsku tutaj. Po polsku tutaj. English everywhere. Can you?
Если кто-то, кому-то нужно по-русски, подходите сюда. Есть это.
So, русский, латвийский, латвийский, yeah, over here,
Jā, sakot bildi. So, tie, kam būtu nepieciešams tulkojums latviešu valodā, ja? Ejiet tajā virzienā, tur, kur rēkojas kolēģi. Jā, re, kur paceltas rokas, ja? Tur ir...
Ok, moi je vais faire cela, mais il faut que je me mette avec vous. So I'll do the French translation. Si vous avez besoin d'introduction en français, s'il vous plaît, allez par là avec ce groupe. Et il y aura introduction en français sans microphone, juste là-bas. English everywhere, français par là, polski, latviski, ruski. Do we need any other translations? Wer spricht nur Deutsch? Okay, there's no German translation. Castellano? Italiano? From Tesli, so welcome to everyone on behalf of the Tesli meeting in Riga, and a very special welcome to Professor, he's got a complicated name, Vyacheslavs Kashcheyevs.
Thank you, that was perfect.
Who's a specialist in quantum physics and nanotechnology at the University of Latvia. And he's going to talk to us, and then there'll be time for questions and general discussion. And the theme, it's how a scientist looks at the universe, the creation of God. So maybe I'll hand over to you.
Thank you very much, Jean-Marc.
Thank you.
So, good evening, labvakar, dobry večer. I'm really feel very, very special to be in your midst and see this crowded audience. The reason I put this particular church on my first slide is also very personal and special. That's the place where I first heard about the and that's Lutheran Church of the Redeemer in Old City, Jerusalem. For several years, that has been my home congregation. These were the years when I studied and did research for my PhD, my doctoral degree in physics at Tel Aviv University. We commuted every other Sunday to Jerusalem for services and communion. I'm a physicist, a theoretical physicist, and I will tell you. First, I would like to establish a few things what physics is, what the particular way how it's a particular way how the Creator reveals Himself through the physical world, through the mathematical laws that are apparent in this world. And then I will try to convey to you the sense of wonder that those particular examples, of those few discoveries of physics during the last few centuries that have spoken to me personally very strongly and helped me to appreciate more the world around us and the way that God has arranged and created. So that's the plan, right? I know there are translations going on. I will try, if there are some complex terms or phrases, I can repeat them in Latvian and in Russian, and I trust the other languages will be coping well. But if there's distress, right, so the translators show me signs, don't worry, right? And of course, and I'm looking forward, and it's usual if you ask a professor from the university to give just a short introduction, it also goes on and on and on. And with theoretical physics, that's very, very frightening, right? So we have a safety mechanism, John Mark, right, who will also show certain signs of, oh, okay, right? And I do look forward to the discussion which will follow, but to have discussion, I need to offer you something, right, just to start. Okay, so then let's start, and let me start with a picture and a formula, almost like in your science class. And I think, well, do you raise your hands who have seen this kind of formula or learn about it? Amazing, isn't it? Right? It must be something very, very important. Yeah, of course, that's the Newton's law of universal gravitation. And there are very deep reasons why this law in every country's textbook of physics, because I would say Newton's fundamental discovery 3 centuries ago, at the end of the 17th century, more than 3 centuries ago, getting old, have in a way defined what physics is. And let's see what's important here. So this is a caricature, of course. That's this well-known anecdote, which probably never happened in real life. Apple falling and kind of prompting Newton to think of this gravitation law. The importance of the first quantitative universal law discovered was that Newton has discovered a unifying reason for very diverse phenomena, like why are the orbits of the planets around the sun of particular shape, circles and ellipses, why all things fall onto the Earth, why there are tides. Here in Latvia, the Baltic Sea is quite shallow, and the tides are not that pronounced. Those of you who live near the ocean, have visited the ocean, know that the water rises and recedes regularly. And the big discovery that all those phenomena can be put into a concise mathematical form has had a profound effect, of course, on the history of science and on the mankind, but also on Newton himself. Newton was a deeply religious man, and to him the discoveries that there are uniform, universal laws governing the natural phenomena, that those laws can be expressed and understood by the way of reason and in a sharp mathematical form, to him that was the vindication of a creator, almighty creator who is reasonable. So that was quite a turning point in the way physical world is seen. There is some order which we can learn, and there is a way, a particular special way to learn about how creation is organized and how things happen and have happened before. And but also it was not only this powerful realization, wow, there are things which are revealed to us by reason, but also simultaneously Newton has set the boundary of physics. And this is quite an extended quote, but this is the particular place in his writing when he actually very clearly defines what he was calling natural philosophy, which later came to known as physics, as something which we can conjecture and then confirmed by experimentation and observation. And here he answers a particular critique of his other scientists of his age, which was they were saying, look, you did not really explain gravity. You did not really explain why planets go circles around the sun, right? Because your explanation, although it's beautiful and unifying, it still says that, well, that's because there is a force described by this or that particular law. But why is the force? Where does this force come from? And that's where he has set the boundaries that, well, physics eventually gives answers about how things work. It never really answers the fundamental why things are that particular way. Although the answer is
the answer eventually to the question of how, the questions which motivate physicists remain people in full sense of that word. They're not machines, right? The most fundamental discoveries in physics have always been motivated by the question, why? Why those particular shapes? Why apples fall? Why there are tides? So it's a certain philosophical circle that we start with the question of why. We may get answers to that, which are on a deeper level, which reveal something important, but eventually the nature of those answers is describing how things work. Let me show you a particular example. We fast forward 2 centuries ahead. Another great mind, another person through whom deep secrets have been revealed, Albert Einstein, in the beginning of the 20th century. He was deeply pondering one of the questions that Newton could not answer, why. You know, since there were so many hands up, there was a law about, there was one law of gravity, the force of gravity, which you saw. There was another Newton's law, which also has force and mass in it. Anybody? Another Newton's law, not the one of universal gravitation, with F and M? F equals M times A. F equals M times A, right? Newton's second law, the main law of motion. It describes how masses respond to force. And Einstein's deep question was why it is the same M? Because these are entirely different phenomena. One thing is inertia, how difficult it is to change my state of motion. That's my dynamical mass. That's the mass from the F and A. And the other mass tells me how strongly I attract you. Physical, there's nothing, just purely physical, right? Don't be misunderstood, but you have M1, I have M2, we can put it in the formula, we can compute the force. Why? Those two quantities are always the same, they're always proportional to each other. And the amazing thing was the set of equations, which are much more complex than the one you saw before, and which reduced to them in very special, simple cases like Earth around the Sun at low velocities. These are the laws of the so-called general theory of relativity, but that's essentially an advanced version of the law of gravity. And those laws have been proposed by Einstein and confirmed spectacularly, they're very accurate observations. Here's also another very important thing about physics, which gets often misunderstood. Einstein never cancelled or somehow repealed the discovery of Newton. It is just in very extreme limits the things happen differently. So Newton's theory of gravity is still valid, good, and solid, but it's an approximation. And Albert Einstein developed a better approximation, and that has revealed a fantastic thing. Now I've stopped talking about formulas, don't worry, this is the last formula of my slide. It's getting easier, there'll be pictures and so on, right? So hang on with me, right? What story, you see also, those dry physics answers, they never contain stories, right? They're just measurement, theory, whether they agree or not. Stories are within humans, right? But here, mathematics itself contains a specific picture, specific story of how the world around operates. And the message here is that the space, or this where we can move and where we live and where all those laws of physics apply, is not just nothing. It's like a canvas, like something which can be deformed, something which can have ripples on it. And when we have matter, like planets or us, more rarefied matter, like air or light, all those forms of matter, they deform the canvas. So the paint is all forms of matter, and the canvas is this space-time. And the left-hand side is how this space-time, or the canvas, is deformed, and it's exactly proportional to the properties of mass and the way the mass moves. And this g is the very same constant from the Newton's law. The reason I've chosen this particular example is, and speaking about gravity in particular, because gravity is the force of the cosmos, very technical sense. It it is decisive and the most important force on a very large scale. And the reason, again, is very simple, because other forces known in physics, they tend to cancel on larger scales. Like if we have minuses and pluses, that they tend to combine to neutral things, like the electrical forces. And gravity is the only force which is long range. The more mass you have, the stronger the gravitational force. And that's why astronomical structures and the universe at large are governed by this particular force and this particular equation. So what has this equation taught us? I'll show you two examples. One of them is very recent. I even mentioned that this morning on national television. And I think, yeah, many people have, well, live here. You don't have to go to YouTube to talk to me about that. But this was all around the news in the beginning of this year. On September 14, 2015, ripples of the space-time vibration have reached the heavy mirrors of the LIGO Observatory, which is the Laser Interferometric Gravitational Observatory. And here you see the imprints of those ripples. And those ripples happened almost simultaneously in two laboratories, many hundreds of kilometers apart. I could go on, I could deliver a whole lecture about this. The reason why this discovery was particularly appealing to me was that as a youngster like you, I read books about gravity, Newton, Einstein, about black holes. Black holes are such dense concentrations of paint that they burn a hole in the canvas, right? That's why it's a black hole. It's something where so much paint, you can put it in, but cannot get it out. And I was trying very hard to imagine this object, to learn about its properties from equations. But I never believed in my life that one day there will be a confirmation this is not just theory. And this signal was exactly that confirmation of Chile. A completely catastrophic event which happened 1 billion years ago, which was the merger of two black holes. But not to be carried away too much by the gravitational waves. Fortunately, these waves were so weak, so feeble that no damage has been done, no human was hurt, right? Okay, let me show you something which may be even more profound, but which was all the headlines just several decades before. Even I think when I was your age, I think that was when the first these data were taken. And that's getting a little bit serious. Let me just be very clear what I'm trying to say here. So the power of this concept of space-time filled with all kinds of material objects, in particular, and that was the new way of discovering things by the way of Einstein's theory of gravity, was that you can try to apply, approximately, those equations to the whole space, to everything. Let's see what would happen if we apply those equations to everything. And by the middle of in the second half of the 20th century, several lines of evidence were pointing to a startling discovery that the physical universe, the one that physicists have been observed, studied, and discovering all those laws, has not been like that eternally. That's like Einstein would like to have it. No, it has had a beginning. So it was a completely physical discovery of the fact that this world, as we see it around us, has had a creation of it. It has had a well-defined beginning. And it was really hard for the physicists of the day to accept that fact. Einstein himself did not derive the proper solutions to his equation that can be applied to the whole universe, because he believed, it was assumed without evidence, that the universe should be static. So he did not accept a dynamic universe. The universe where galaxies recede, where space itself expands. So the canvas is not static, it expands, right? And the picture gradually, slowly changes. Fortunately, we are all safe. It happens very, very slowly. But coming to this crucial picture here, as always in physics, in this dry physics, there are data points, there are measurements. Einstein's discoveries was that light travels at finite velocity. So the further away are the objects that I'm looking at, the older they are. There are stars relatively nearby, roughly 2,000 light years away, which if we observe them now, we see the light which was emitted during the time of Moses, which is incredible, right? Stars further away are even older and older and older. And then, of course, this big why, which motivates, I think, not only physicists, and what's the furthest that you can go, right? The further you go in distance, the oldest things you see. What's the oldest things we can see? The oldest things we can see is the light of creation, is the cosmic microwave background radiation. It's all around us. It was discovered actually by accident. It was discovered by two radio astronomers who were building the most sensitive radio telescope. And they could not get rid of the noise. Every day they would be getting the noise no matter where their antenna is putting. It was like hiss all the time. The same noise, the same light of creation can be seen on all television sets. Probably you know televisions as flat screens, right? Something like that. But please raise your hands who have seen CRT, those tubes kind of television. No, not that little, right? If you switch that television where there is no transmission, no other radio waves, there is this black and white noise. Half of that noise power is to reveal how much energy is depending on the frequency of the wavelengths. That was the measurement. And it was done in, this accurate measurement was done in space, where atmosphere doesn't interfere with the signal. And to me, the most amazing thing is that those data obtained in a very hard work of many tens and hundreds of scientists, they all fall with an exquisite precision onto a simple curve which can be predicted, putting together Einstein's equations, the properties of the atoms which have emitted this light, and the exact number of years that have passed since then. So that to me was a very special thing, that we are allowed to learn something about the very beginning. And nowadays, physicists keep making more accurate observations, and they study tiny deviations of those points. So actually, that's the first image of the universe which we can see. It's slightly homogeneous. Then again, there are theories to be tested about those things. That's the part of physics which is called cosmology. And it relies on the same laws which we can discover here on Earth and near Earth. Let's see. Okay, so just maybe 5 to 7 minutes, right? We didn't start on time. I was advertised as an expert in quantum physics and nanotechnology. So that the 3 slides just to kind of justify, vindicate, right? Even if I'm not a gravity physicist or astrophysicist, it doesn't prevent me from being fascinated by those discoveries. That you don't have to be physicists to be fascinated by them. I think there are no boundaries, right, in knowledge. That's what's beautiful about the world. So quantum physics. Well, that's not even a lecture. That's a minimal introduction would be 4 credit points. So I won't pretend I can do a proper introduction to quantum physics. But what is that about? It's sort of opposite to cosmology. That's the smallest scale that we were able to learn solid, exact things about. And that's the ultimate microscopic reality. And the very big discovery, which was made in the beginning of the 20th century, which is actually the first physicist who has realized that light is also composed of discrete portions, or so-called quanta, was German physicist Max Planck. Hooray for Germans here in the audience. Actually, the space mission, which was, sorry for jumping back, but the space mission which produced that plot is called Planck, in the honor of Planck. And this curve is the Planck's law of radiation. And it is necessary to take into account this particle nature of light to derive it properly. So there are fundamental elementary portions of matter, which are known as atoms, electrons, which are quantum, and you sensitive, and you set up the experiment precisely. The three things I want kind of you to remember about these elementary things. There's usual